Thank you very much. So, so yesterday I moved one problem from one problem to another. I mean, towards the isomorphism version of Anabelian conjecture. We also needed to consider the problem of automorphism group of varieties. And then I introduced two objects for the augmentation group, augmented profinite fundamental group. Namely, I introduced so this is just a general setting. And and consider we have a natural exact sequence as usual. And still I omit the mentioning on the base points because I just want to consider the extension structure of this part. And then I compare two objects. One was I wrote EKX. This is the automorphism group of this the middle group inducing identity on the Galois group, and modulo the image of the conjugation by the normal subgroup of here. And another was I wrote out GK pi 1 bar. This is a centralizer of the image of phi out of the representation. Then there is a fundamental exact sequence connecting this and this. Namely, the difference is represented by continuous cohomology group of GK on the center of geometric fundamental group. This is a Wells exact sequence. So, and we have a natural image into both object from automorphism group of Xi. So this is a geometric automorphism group. And we expect in the case of hyperbolic varieties, which should include Anabelian varieties, this must be finite group. So it is okay for all hyperbolic curves, and also in the dimension bigger than 1, if X is a general type or complex points form Kobayashi hyperbolic space, then automorphism group of the variety is a finite group. So if we can expect this object is reflected in the fundamental group, then perhaps either of these two could coincide with this one, or at least the image of this thing may reflect this finite group. This is a very naive expectation for Anabelian varieties. Then,
Can you remind me what let's get the definitions of hyperbolic confused. Can you remind me what Kobayashi hyperbolic is?
Yeah, yeah,
It's the one
yeah,
above.
oh yeah, yeah. So this is still, yeah, in the higher dimensional case, I don't, I didn't give definitions, but
Like, is this the one where you have no non-constant map strings, entire map strings?
in
Or is it with
Complex cases.
a complex case, but Kobayashi metric is really distance. Then it gives Kobayashi some.
Measure distances by mapping little bit.
Yeah. You can.
Oh, so I'm thinking of the other
Yeah,
definition.
yeah, so, yeah. So,
You want that to be a distance.
okay, so.
Little distance.
There are several
Okay, I think I'm
senses,
voting
but
for the top.
yeah, but
That's the same in most,
okay.
in many complex cases.
Yeah, complex cases there are some. I think Kobayashi metric is treatable, but maybe another definition like Royden metric or something. There are several ways to introduce hyperbolicity in complex geometry. And maybe in the algebraic geometry, perhaps log general type or such thing. Then, anyway, in those cases, finiteness of automorphism group is proved. And so, first, I want to give a bad example of hyperbolic variety, but not Anabelian, or not pass the Anabelian test. This is a joint work with Ihara. So I consider AGM to be the it's defined over Q mu m, the moduli space, moduli scheme of polarized, principally polarized abelian variety. And with level structure greater than or equal to 3, then this is becomes a smooth variety, and usual expression over the complex points is Ziegel modular group modulo Ziegel upper half space modulo gamma gm, and gamma gm is or maybe is the matrix acting on the this space, but imposed this condition, congruence modulo modulo m congruent to the unit matrix. Okay. Then in this case, so pi 1, geometric pi 1 is a profinite completion of this group. Yeah. But the result of Bass Lazard cell told us any finite index subgroup of this one is coming from those congruent subgroup. So this isomorphic to the so just I take a finite index, so I have to take if P divides M, then this is rather exceptional, and most of component of P is P to G dP. So profinite completion decomposes in some finite number of thing, and also this periodic group. Then in this case, center.
So this is for G is 2? For G
G, yes. So yeah, I have to mention perhaps, yeah. G 2. This is important. Then the variety is dimension is bigger than 1, and this result pass Lazard cell and called the congruence property. I think, yeah. Okay. And it proved in 1967 in publication of IHS. So we have lots of center here actually. So so center of pi 1 bar is very big. So includes so maybe at least all. Sorry, excuse me. So this is prime to m part. So this is infinite. So in view of this exact sequence, already here we have lots of elements, and so EKX cannot approximate finite group. Sorry. Z mod. So okay, so how do you call it? Yes. I'm sorry. So plus minus 1. So this is already, and then next I want to consider this thing. Actually, for this Shimura model, we have Shimura's model for the extension for modular functions for this thing. So yeah. Okay, so we have let LG to be the all union of all function fields of this. Maybe K is not big. So all such thing. is a function field of all modular functions. And then okay, so we have such exact sequence for this, so LG over function field of the bottom one. So then so just the constant field is this thing, and the geometric part is just the kernel of this. So just then the fundamental exact sequence can descend to this exact sequence. So we have pi 1 of m and and also pi 1 bar. And we have a natural surjection here. So and okay, so but but the okay, above sequence is the same as the following. So so actually, so yeah, so yes, the point is the this group. Yeah. Perhaps, yeah. Okay, sorry. Okay, the point is the level 1. So this is canonically isomorphic to GSP G hat modulo plus minus 1. So and the right arrow gives only the similitude character. So from here to Z hat prime, this is just the similitude character. So so and so the outer representation we have to take first take element here, then inverse image of here, then conjugate action here, and but we can take element of here. We can take the inverse image of such thing. So then take conjugate action. Conjugate action on pi 1 bar. Yeah. Then everything is written in the terminology of matrix, and one can show. So see this. One can show by using the centralizer of this SP part in inside the GSP is only scalar matrix, and but so and the action conjugate action of this to here modulo inner automorphism has image. So okay, so we have anyway we have phi of g q mu m to out pi 1 bar and but I just identify this thing inside this one, and then we have conjugate by this matrix. Then it factors through factors through actually so over dt double. Yeah. Makes sense? Makes sense. Excuse me. Yeah.
In the Shimura's model, so this geometrically gives you pi 1 bar. Is that in the kernel? Is that an isomorphism? Is that
Yeah.
there's an
Pi 1 bar is here. Yeah, isomorphism. I'm sorry. Yeah, this is isomorphism. Just everything is descending over this. So still, this is infinite. Yeah? Infinite image. But unfortunately, the image is not only infinite but also abelian. So the centralizer of the image also includes this infinite image. So in this way, we can see this group is infinite, but also the image of this one is also the image of this also include this infinite image. So this way we can see this G-Gale modular variety is not a good candidate for Anabelian chain.
Why did it factor through this?
This one, yes. Actually, it's a little bit you need discussions, but so this one is essentially come from scalar matrix of. So scalar matrix is by conjugation act trivial. So if you take also here A, then the image is A square. So if you from here you have such thing, then this goes to A square. So if A is a square number, then it doesn't give non-trivial action on conjugate. This is a bad example.
So if I understand the definitions correctly, there are other, they're very simple hyperbolic varieties that are also non.
In a similar way.
If I take a hypersurface of high degree in Pn.
Hypersurface?
Then just because the fundamental group is
the same.
trivial, then
Well, Yeah, but perhaps in that case, k pi 1ness fails for such thing. If you take some hyperplane section, then yeah, this at least for complex sense, this is k pi 1. So Anabelian test, I didn't make precise formulation, but perhaps k pi 1 is also we need, and also from this example, center triviality, or also we have to expect maybe the exterior Galois action has infinite image, and the image is also very non-abelian. Yeah? So if the image is abelian, then so there are three tests: so center triviality and k pi 1 and maybe the Galois image also. Yeah.
Do you know how the descending central series of
This group?
Yes.
I think it's not.
That's finite.
Yeah.
So it's like
Subset some.
It's not a very good. Yeah. So thing, but
So
yeah.
my question is this: do you have an example of a scheme whose descending central series of its fundamental group doesn't stop at any point, but is still not Anabelian?
Still not Anabelian.
Yeah.
So this is one.
So this is
This
yeah.
one.
The time regarding
Yeah.
you were
Yeah.
I guess if you take yes.
Yeah. So this, if the descending central series converges to 1, then you have a all thing almost nilpotent. But I think this group has not nilpotent quotients. Yeah.
If you look at the SP
G.
GL, where but only the congruent subgroup L, which is the one which occurs,
Yeah.
that's a parallel group of the congruent.
You mean so SP to G over Z?
Yes.
Yeah. But this is not.
You want to take the congruent subgroup.
Congruent.
So ZL, L-adic,
L-adic.
the congruent subgroup, congruent to 1 when you go L1.
The level L subgroup.
It is a parallel group.
Ah, yeah. L-adically.
So the central cell.
I see. Yeah, it's true.
But at L11 you will get something finite.
Yeah. So you have to choose one L. So in this case.
One of the L divided.
Yeah.
Is this finite number? Well,
No, it's get bigger and bigger. Hold it.
QL nilpotent conclusions.
Yes.
Series is bounding something depending on G.
Do you
So
perhaps-
that's an analytic. It's a Lie group of dimension. Maybe not some
But
can
in
write
the
down more.
algebra, tensor as well.
But this is what they say. The central series is fine.
No.
Pro M. Or the Z is more.
you don't need to take profinite completion in your question. Then, okay. But if you take profinite completion, then
I'm just thinking that if this condition that the descending central series never stops is a good condition for being Anabelian.
never stops. never stops.
I mean for all L.
So, should finite covers of Anabelian varieties be Anabelian? Finite unramified covers?
They are Anabelian, right?
Sorry?
They are Anabelian, right?
No, Anabelian.
Anabelian bracket.
Yeah, should they be closed?
Yeah, I think so. So, okay, so, and yesterday there was a big discussion on the center triviality of profinite groups, and
Sorry, I have just one more question. In Groth's letter, does he say that Anabelian things should only depend on complex points or something like that?
yeah, I have no idea. Yeah, but
He says something
perhaps
like that
yeah.
Anabelian should only depend on complex points. Your condition definitely goes against
It
that.
looks so. But well, but it's only one example, so
No, that's
yeah,
true, but
that's
if your
the-
condition
yeah.
involves the Galois image,
but k pi 1s also can be considered as a étale topology, no? I saw, and maybe it's not the same as the usual k pi 1.
I think that what he says hints at what should be Anabelian is that the moduli spaces should be, without any specific arithmetic, should be Anabelian.
Okay.
any of them are right.
Moduli spaces of pairs are Asymmetric.
Yeah,
Other
yeah.
ones are
For big, no, for big, yeah, for big genus
Yeah.
and raise enough
Okay.
points.
So okay. Anyways, so center triviality. So yesterday I checked the some literature. Then the anyway, profinite completion of free group is studied by M.P. Anderson. This is topology, and surface group case was proved by Labotsky, Van den Dries. This is Israel journal. But yesterday this problem was very involved, and so Dr. Majid Hadian gave a simple argument for this using geometric idea. And I think their proof is not using geometry as a combinatorial group theory. And actually, I studied such phenomenon in the combination of topology theorem by Gottlieb, and in the discrete case, if discrete group gamma is type FL, this is trivial module Z has a finite length free resolutions over the group ring, and also Euler characteristic is 0, then Gottlieb theorem tells the center of gamma is trivial. And if we want to discuss generalize his argument to profinite completion, then we need to put also goodness of in the set of cells. Then we obtain profinite completion has a trivial center. So in this case, at least virtually these two conditions are satisfied, but unfortunately the eigenmodular group is not good, so has lots of center. And also this condition, if once gamma satisfies this condition, then all finite index subgroup satisfies this condition. So the property inherited to the finite covers of such thing.
What means gamma is type FL?
Type FL is so look at this as a trivial module of group ring. Then this has a finite length resolution. And all Fi is a free Z gamma module. Obvious, opposite, yeah. Sorry, the resolution. So free resolutions. Of finite rank, yeah? Free finite rank.
Does this imply that gamma is finitely presented or something?
Finitely presented, I think it was not assumed to prove this theorem. But if you have you have finitely presented, this condition means it's homotopy equivalent to so k gamma 1 is homotopy equivalent to the finite complex. Okay, so I think, yeah. So this modification I made in my thesis, yeah. University of Tokyo.
Oh, I see.
Yeah.
So if gamma is finitely presented, maybe you can give this geometric proof again.
Hmm?
If gamma is finitely presented, maybe one can give this geometric proof.
No, I don't use. I used only algebraic tools by Stallings. I called Hattori Stallings trace or such thing. So yeah. So I should perhaps mention Stallings. Yeah. Yeah.
He couldn't see any way to do more elementary homological algebra. So suggesting this
Yeah. Yeah. Yeah, so Gottlieb perhaps use the geometric argument, but Stallings use only this thing and very algebraic argument. So I could use just interpret it under the condition of goodness. So, so in this respect, perhaps center triviality of all open subgroup maybe of all open subgroup of pi 1 bar one of the
So it's to be
conditions.
expected that fundamental groups of Anabelian variety be good.
Yeah, so I think, yeah, I'm not sure. Yeah, but because of that, so in characteristic P, also, yeah. Yeah, so, yeah.
I don't know, I mean, I just wonder what people expect.
Yeah. But for example, if MGN modular space of curves, then mapping class group, the fundamental is not known as a good group. So, and many or some people wants to try to prove this, but I think.
Should be Anabelian. But it should be Anabelian, whatever the definition is.
Grothendieck wrote some such expectation in his.
Grothendieck says that category of an Anabelian scheme was contain all curves greater than one modular space of the curve, and if something is an Anabelian, any fibration by curve which is greater than one will that must also be Anabelian.
But that doesn't answer the question of whether the modular space is great.
No, they are Anabelian. Modular
Okay,
space.
that's,
Expected.
but I mean, okay, what is expected once you have a definition?
Well, we just maybe at this stage, yeah, no.
Actually, maybe there is there a recipe if somebody gives you the mental law, say, look, this is of some NPN. Is there a way to find out what is G, what is N, and maybe to reconstruct?
Say that again.
From the fundamental group, is there a way to this to reconstruct somehow?
Or G sufficiently?
Yes.
Why?
But I don't tell you what is G and I don't tell you what is N.
Why?
So you're saying, can you construct
Can you distinguish them?
G and
Easy, we do
N?
it
I
for small
suspect
G
you.
as well.
It's the stuck, of course.
Mm. Mm. Okay, so
Oh, sorry, can I ask when you this sentence on the left, center trivia, the center trivia,
T of
this is for the pi 1 bar of curve.
pi 1 bar of curves is, yeah, it's okay, yeah, okay. Because this thing,
Yes.
and this property is called slimness by Mochizuki. So,
But this effect on this interpretation, do you really need free resolution or projective resolution?
in my proof, I used essentially free resolutions. Yeah.
In the topological paper, Stalling just uses projective.
Really?
Yeah, but I can see why you assume free, because you want to take completion. But anyway, Stalling just uses projective.
I mean, the conditions I told.
Sorry?
The conditions I told.
I'm not sure.
Okay, so this is a counter example for Anabelian. So maybe I want to change the topics from here. So maybe episode 1. So let's back to the hyperbolic curves. Yeah. Curve C of type this thing. Then in this case, as mentioned there, we have centered trivial geometric fundamental group. So we expect automorphism group should isomorphic to EKC, or and this is the same as the centralizer of Galois image in pi1 bar outer representation. And actually, so this question was already established by Tamagawa and Mochizuki. The result. And if I could prove for genus 0 curves, then I could get the isomorphism version of this result. But unfortunately, we needed to wait for their contributions. But we can also consider we could approach a Proel version of this thing. So in this case, the previous results of genus 0 case, I couldn't prove instead. But for this expectation, so L version.
No, when you mean Pro L is geometrically Pro L or everything?
Geometrically Pro L. Yeah, excuse me. So I just consider the maximal Pro L quotient of geometric, and Galois group I keep from the previous. Then, but this actually also by Mochizuki's result, because Mochizuki proved his result for local Pro-P conjecture. So local. So very strong result. So this expectation of a Proel version also follows from his result. But before that, so this is only episode 1, so still several steps until their contribution. So I wanted to approach this Proel version from more naive tools.
Excuse me. Sorry. Following up on Florian's question. If you make everything Pro L, is it
No. So GK is the same as.
I know, but
yeah.
is it very bad if you make everything?
If everything is Pro L,
Then you will destroy a lot of the
Yeah.
geometric.
Also geometrically, we don't have.
Sure.
You do not have geometrically, you do not have points but patches.
Doesn't obviously bad.
For most L, there will be nothing there. Because you have this symplectic group.
Oh, I see. Yeah, I see.
So, but I spend almost
Roots of unit.
times.
Pro L.
Except if the points are rough.
Yeah.
Okay, so maybe that's as usual. I just want to expose simplest question. Whereas so C is C1 minus 3 point. then outer automorphism group of phi1 bar. In the simplest case, such thing can be expected. So this is actually for my result. This is also very old result. And in this case, so pi1 bar L is a free pro-L group. Rank 2, and so it's x, y, z, and x, y, z equal 1. And x and y and z is the loop rounding 0, 1, infinity. Then we have outer Galois actions of GK. And the action preserves the conjugacy classes of these inertia groups. So the image of phi is inside some blade-like outer automorphism group. This is all automorphism of pi1 bar L, and so alpha respects the conjugacy classes of this. Here. And modulo inner automorphism. Okay. But also we have characterization of inertia subsets in this fundamental group. So also we have also this the centralizer of Galois image is also have to here up to so okay, so we are okay, so if we change if we apply symmetric group of third degree, then this has to be inside here. Okay. So now almost the time is coming. So, yeah, so
What's K?
K is just number field. Yeah. Yeah. So in the case of pro-L fundamental group, we can use the technique of lower central series, and then we can prove the finiteness of this thing and isomorphism with this finite group, but unfortunately I have no time to expose details of this thing. So yeah, so perhaps I postpone the details tomorrow, or just omit. But yeah, so maybe using lower center series, but I should explain. I should like to explain, but so maybe. And also this result, the method also can be extended to the other curves or configuration space of curves. So, so maybe just a question. So, is whether the reversion of this should be proved. So, if we replace, so we have Proel version, Proel fundamental group, but we can consider maybe pro-unipotent completion of this thing. Then we have Galois actions of GK, and question is whether the same thing can be held. And I think someone already has proved, but I haven't heard such thing, because in this case we can use also here lower central series, but we don't have characterization of inertia subsets. So in this way, maybe some detailed information on the Galois image of deeper filtration should be necessary to prove this thing, and I don't know. But I think this might be open problem. But Professor Dorini gave me a letter in 1993 or so. I don't know, you don't remember perhaps. But if you consider, if you replace C to M0n, so higher dimensional one, then we can prove the reversion of this thing. If n is bigger than 5, yeah? This is okay. So I want to explain why higher dimensional reversion is okay, but one dimensional is still open a little bit tomorrow. Yeah. I'm sorry. I prepared lots of things, but only very small thing I could talk today.
What's the difference between n equals 4 and n greater than or equal to 5?
So this is only free group, yeah? Free group, yeah. But this has a lot of relations. Yeah. Then if you use these relations very in a trick way, and then the automorphism of group of the graded real algebra of this thing can be computed very small limitations. So then we could prove this one. But in the case of free group, it's very difficult. So I should, in the case of n is bigger than 4, so in this case, higher dimensional case, we can characterize the lines generated by inertia on this Lie algebra. But here only free group, so there are no tools to do such thing, characterization. Okay.
This section talk about high dimension, one more time. Lie versions in general.
Lie versions in general, so for configuration spaces on the Proel version is already okay for higher dimensional case because of so using genus zero cases also we can reduce reversion of configuration space to one-dimensional case and reversion. Reversion is so I think this is perhaps this is okay, but in the higher genus case only few cases we have. The Proel case Proel case for configuration space it's already established, applying Mochizuki result and some reduction. We can reduce the configuration space case one-dimensional case, but one-dimensional case reversion is so only limit. This is still open, and in only limited case we have results. Only limited case for the reversion of one-dimensional.
So can you tell what was that?
So so it's elliptic curve minus 1 point without complex multiplication, or complete curve of genus 2 or more with Galois image is open in symplectic group in Jacobian. So it's okay, but for other, if you have lots of punctures, then you don't have inertia characterization, and also so it's.
But if you consider, for example, just one puncture.
Just one puncture, I think it could be approachable, but I still don't make assure myself, because it's depends on the centralizer of symplectic group in general linear group. I don't know.
When you say that the image of the Galois representation should be as big as possible?
As big as possible, and then so my approach is first using a weight argument. This centralizer have to be embedded in the action on H1. Then after that, the image should be restricted by smaller group by using the information that acts trivially on deeper Galois image. So that's it, and so Yeah, well, maybe tomorrow I should explain. If I like